We got a very exciting announcement in the last couple of weeks, and that was that JWST has detected the presence of methane in the atmosphere of an exoplanet for the first time. And, methane is cool. It's not that exciting and not that crazy. I mean, there's methane in the atmospheres of Jupiter and Saturn and Uranus and Neptune. It's on Titan. So methane is out there, but it's on very cold worlds. This planet, WASP-80b, is a warm Jupiter. It is hundreds of degrees centigrade. It's not the thousands that the hot Jupiters are, and yet it was kind of surprising that there would be the presence of this methane. So my guest today is Dr. James Bell. He is a postdoctoral researcher at the Bay Area Environmental Research Institute at NASA Ames. We talk about the discovery of methane at WASP-80b, and then just carry on the conversation into the tricks and the techniques and how researchers study the atmospheres of exoplanets, what the future might hold for this field. It's a fascinating conversation. I think you'll really enjoy it. All right, here's the interview. Tell me about WASP-80b.
So this is a unusual planet. It's a planet that has about half the mass of Jupiter, but is about the same size as Jupiter. And that in and of itself isn't too unusual. There's plenty of those planets around other stars. But what's particularly unusual is that it's orbiting around a star much less massive than our sun. It's orbiting around what we call an M dwarf, which is a low mass, red colored star, which, there's almost no giant planets around these types of stars. They're quite rare. And so in and of itself, it's, intriguing, unusual that there's this planet, but it also presents an excellent opportunity to study the planet, because a lot of the methods that we use to study exoplanets, require a large planet around a small star, or like you get better signal when you have a large planet around a small star. And so this planet offers a really excellent opportunity to, study a planet in detail.
Do we have an analog? What's the close example of what we have here in the solar system?
Jupiter and Saturn are, same-ish size as the planet. This planet's a little bit more massive than Saturn, a little bit less massive than Jupiter. It's kind of in between those two, but it's much warmer than that. It's several hundred degrees, and so it's
it was described as a warm Jupiter, right?
Mm-hmm. Yeah, so it's not a cold Jupiter like our Jupiter in our solar system, and it's not a hot Jupiter, which is the kind of exoplanets that we typically study. It's kind of this in-between regime, which is, an exciting place that we're being able to study now more with JWST.
I mean, give me some context here on, you say this is very rare. We think about those M dwarves. We're familiar with, say, the TRAPPIST-1 system, like all of the Earth-size-ish worlds that are orbiting in the habitable-ish zone around these exoplanets. We're finding them around M dwarfs, and partly that's Kepler, because Kepler had to switch to its mode where it was only able to view M dwarfs because of its loss of reaction wheels. But is this like an extreme outlier that you've got a planet this big orbiting a star that small?
Yeah, so I can't remember the exact statistics off the top of my head, but for rocky-sized planets, the average is that there's roughly one or more rocky-sized planet around an M dwarf. That's not too uncommon. Meanwhile, it's much less common for Jupiter-sized planets. Again, I don't remember the exact statistics, but it's more like 1%. So which is fairly similar, I believe, to other larger stars. Stars fairly independently of their stellar mass have about 1% of them have Jupiter-sized planets. But these smaller stars have a lot of rocky planets.
And the big discovery, and the one that I saw in your preprint article, and then I was asked to wait, was that you had discovered methane in the atmosphere of this planet. What technique did you use to find the methane?
Yeah, so we used two different techniques. We used the transit spectroscopy technique and the eclipse spectroscopy technique. So, transit spectroscopy, you have an exoplanet transit where the planet passes in front of its host star. And so, some part of the planet is just completely opaque. It passes in front of the star, blocks out some of the starlight. And so that is just a standard transit. But when you get into transit spectroscopy, you're looking at kind of shades of gray of the transit of the the, the atmosphere of the planet. The planet's basically all gas, but some part of it is transparent enough for some of the starlight to pass through. And then some of that light will get absorbed by certain molecules. And so, yeah, as the light filters through the atmosphere, it might bump into some molecule, get absorbed at that particular wavelength of light, but a nearby wavelength will just sail straight through the atmosphere. And so then we can look at how much starlight gets blocked as a function of wavelength. And that tells us about what's in the planet's atmosphere. So that's transit spectroscopy. On the other side of the orbit, when the planet goes behind its star from our perspective, we get an eclipse. And here we're going from seeing light emitted from the star and emitted from the planet, all mixed together in one big blurry blob. We can't see them as separate objects. They're all one blob. But we go from seeing the light coming from both of them to just the light from the star. And so that causes a tiny dip in the total brightness of the system. And by kind of comparing in and out of eclipse, we can say how much light was lost when the planet went behind, and therefore how much light is the planet emitting. And eclipse spectroscopy, again, looks at that as a function of wavelength. And eclipse spectroscopy gets a little harder to talk about intuitively, but basically all objects emit some amount of light. If you break out infrared camera or infrared goggles, especially the like military kind of style that don't have a light, they look at light emitted by objects. And so you can look and you'll see people glowing red because they're bright in the infrared because we're much hotter than our surroundings. All objects emit some amount of thermal radiation. And so by measuring the kind of thermal radiation from an object, you can tell how hot it is, which is interesting. But then again, molecules shape that spectrum and cause either dips or bumps. And so, yeah, again, we measure the eclipse depth as a function of wavelength to understand what the atmosphere is made out of.
It's really interesting that you have these two chances. You have when the planet is passing in front of the star and when the planet is passing behind the star. But I guess when it's passing behind, you get two shots at it, right? You get as it's going behind the star and then as it's reappearing on the other side. Does that give you any different kind of information?
Yeah, so in this particular analysis of this data set, we just packaged them all together and we just compared the two outsides of eclipse to the whole inside. We just observed for a couple hours and captured the whole thing because the planet's orbit is quite short. It's like 3 days. And so it takes 3 days to complete, and it's only in eclipse or transit for a little bit. And so you can just observe continuously. But you raise a really interesting question, and it's one that I and others are trying to do. I haven't tried with this data set yet, but it's as the planet is slowly going into eclipse, part of it gets covered little by little by little, and then it spends like an hour or whatever inside of eclipse, and then it slowly peaks out on the other side. And while it's doing that, slowly getting eclipsed, you can measure the kind of brightness slowly fall down, and then again slowly rise up on the other side. And you're kind of using it to like figure out how bright each part of the planet's day side is. And so you can't visually see the day side, but you can use the star to kind of scan across the planet and understand where is the heat coming from. And so you can say like the equator is hotter than the poles, or there's east side is hotter than the west side, and that means there's probably winds blowing to the east or something like that, which is, it's a really cool technique called eclipse mapping.
That's really interesting that different parts of the planet are revealed or covered at different points. And so you can start to learn not just the overall constituents inside the planet, but actually start to map parts of the planet relative to itself. That's incredible.
Super exciting.
Yeah. So, what did you find in the atmosphere of WASP-80b?
So with these particular observations, we used a NIRCam GRISM, which measured light from 2.7 to 3.5 microns or something like that, maybe 4 microns. I can't remember the exact wavelength range. And
this is on JWST.
The main things on JWST, yes, exactly.
Yeah.
And so the main things that we expect to see there are water and methane. Water is, I think, after dihydrogen, just H2, I think it's probably the most common molecule in the whole universe. It's a really easy molecule to make. It's lots of hydrogen, which the universe is mostly made out of, and oxygen is an extremely abundant molecule as well. And so water is easy. You should see water everywhere that it can form, and that's good that we do. But methane is what we were really excited to confirm was in this planet's atmosphere. Methane is a relatively fragile molecule. It's broken at temperatures that are relevant for most hot Jupiters. Most hot Jupiters are hot enough that they shouldn't have detectable methane. But now that we're getting into this warm Jupiter, we expect, okay, maybe we should start seeing methane, but where exactly will we see methane? What temperatures will have methane? Methane can also be relatively easily broken by UV light from its star. And the abundance of methane depends a lot on what the composition of the atmosphere is, how many carbon atoms there are, how many hydrogen, how many oxygen. All of those together play some careful balance of defining what the chemistry of the atmosphere should be like. And so, yeah, this was one of the first times that methane has been found in a transiting exoplanet using space-based telescopes.
Right. I mean, there's a bunch of qualifiers there, but the gist being, this is one of the first times that methane has been seen in an exoplanet atmosphere.
There are like free-floating planets, which are not really exoplanets. I mean, a planet has to like orbit a star, and so some have found there, and some very young planets have methane. But yeah.
And I mean, like, methane is common here in the solar system. I mean, obviously we have it here on Earth and it's coming from life, but there's methane in Jupiter's atmosphere, there's methane in Saturn. Think about Titan with lakes of methane, of liquid methane. It's very common. And so as soon as you see methane, you don't immediately jump to life made it. What do you think is the source of the methane?
Yeah. So yeah, Jupiter, Saturn, Uranus, and Neptune all have a bunch of methane. It's the primary carbon-bearing molecule in those planetary atmospheres. And so, yeah, like I said, in what an atmosphere ultimately is made up in terms of molecules depends on what it's made up of in terms of atoms and its temperature. So if you have lots of carbon, like enough carbon and oxygen and hydrogen, you'll end up with some mess of carbon monoxide, carbon dioxide, and methane, and probably water. The exact balance of those depends on how much of each of those different types of atoms you have and the temperature. And so it's just these kind of atoms. I mean, it doesn't exactly happen like this, but these atoms are kind of just floating around in the atmosphere, and then they bump into other things, and they kind of eventually make molecules, and they might make bigger molecules, but those bigger molecules are fragile, and something pokes them, and they fall apart. And so it's just kind of what thermochemically happens. It's just atoms bumping into each other, making molecules.
But there's, I guess, a process of creation, the atoms bumping into each other, but then there's also the process of destruction. And so,
yeah, exactly.
Is there does this indicate some kind of process that's going on in the atmosphere that you're getting this methane?
So, yeah, one could take a box and just figure out exactly at what temperature do you start expecting methane at some temperature or whatever, but planets aren't a box. There's all kinds of mixing. They have a hot, permanently locked day side, a cold, permanently locked night side. And there's all this exchange from day to night and from deep to shallow in the atmosphere. And so, yeah, this is telling us how all of that mixing interacts with the construction and destruction of methane and these other molecules. which is potentially suggesting that maybe methane in exoplanet atmospheres is found more at colder temperatures than in these kind of free-floating objects where we see methane at hotter temperatures, but people haven't been able to find methane at similar temperature exoplanets, and maybe that's related to all this weird day-night deep cold kind of mixing. That might be an important part.
But with all of the observations that JWST has already done, they haven't seen methane so far. I mean, was this a fluke of the kind of planet that, you've got this abnormally large planet around this small star? Was that and in the right temperature range, or is it like a difficult molecule to detect in general?
Yeah, a significant component is finding it in the right temperature regime. There's a lot of papers that have already come out have been for planets hotter than this, and so probably we suspected they're probably too hot to have methane, and confirmed that they don't have methane. Some of the colder objects also start having a lot more clouds in the atmosphere, and that can make it very hard to find methane. And this is a very favorable system to find methane. But my suspicion is JWST is just not that old. Like, yes, it launched 2 years ago, but it only started collecting data a little bit over a year ago. And so it's just, it took a lot of time and energy to analyze these results. And I think there's probably several other people that are working really hard and trying to understand all the weird data stuff that happens to say very confidently, we do see this, we don't see this, or we see it at a certain amount. So I think we'll definitely see more. I don't think this is the only exoplanet that'll be found in the next 5 years. I'm sure there's many more to be found, but I think it's early JWST days, and it's a relative niche of it's got to be cold enough to have methane.
Give us a sense of how much time was spent actually on target with JWST on this planet, and I guess the star, really.
Yeah, it's a really good question. It's one I knew the answer to. I could check, but I think it was about 9 hours per observation, so I think 18 hours total. That's what I recall off the top of my head.
And so you did one observation for the eclipse transits, and then one for the eclipse,
one for eclipse, one for transit.
Yeah, right. Because
were
you actually like swapping out your filter? You said you're using, like, in one case you're using the GRISM. Were you actually sort of reconfiguring Webb for one set of observations because it had to be different from another type?
So both of these observations used the F322W2 NIRCam GRISM filter combination, which is a big mouthful, but there's all these different kind of combinations of different things you can do. And so both observations used the same detector setup and just observed at 2 different times. But the way JWST works is you say, like, a year in advance of when your data will be collected, I want to observe this kind of planet. This is the particular planet I want. I want to observe it using this method. Can I please have data? And a big time allocation committee sits down, reads through them, and ranks them, and then give you time. And then it all goes up to the kind of scheduling people, and then it's all computer controlled. And so someone, like, a few days in advance, will say, here's a schedule, alternate between these different things. And so the telescope didn't point at the star, collect a transit, just sit around and then wait for an eclipse, because that would take like a day and a half or something. Instead, it observes 10 different other things, and it might come back to catch the next eclipse, or it might come back in a week or a month or 6 months later. It'll get around to it when it's convenient for the schedule. It's a very different kind of observing than the kind of old-fashioned, you sit there and you point the telescope. It's much more automated and hands-off kind of style.
Yeah. And then for you as a scientist, like, how does the data come to you?
Yeah, so it all gets downlinked through the Deep Space Network onto Earth, and then it's processed by the Space Telescope Science Institute, and then archived on big archive databases there. And then, yeah, we get an email saying your data is ready, and you go and you just download it off the internet onto your computer, and then yeah, they do some amounts of processing for you. So yeah, especially for some types of science, you can just download what they did and basically do science right away. With time series observations right now, you kind of have to go back to the much more raw data and do a lot of more fine analysis. But that's something that we're all working on improving, is just kind of have science ready data available for everyone.
That's the pipeline.
Yeah, the pipeline. So their pipeline is called JWST, and that's kind of what they use. And then I've worked on a different pipeline called Eureka, which uses JWST and a bunch of custom code.
So, you found methane. Do you think that there are other discoveries to be made, other, say, carbon-based molecules in those data, or is there just not a clear enough signal? Like, is there more time spent, or are you kind of done with that data, do you think?
So these particular wavelengths are just a small snippet of what the total data that we are gathering for this planet. This is the F322W2. We're also getting F444W, which is kind of the next long wavelength piece chunk from NIRCam. And then we also have MIRI low resolution spectrograph. So we're going to get all the way from 2.4 all the way out to 12 microns, all together with different instruments. Because we think there's definitely more exciting science to be done for this planet. Water and methane, excellent starting point. But like I said, it takes a lot of time and energy for each of these pieces. And so this was kind of like a good point where we thought, okay, we're confident about this. Let's put this out there. It's exciting science. But yeah, the next NIRCam filter is going to look after things like carbon monoxide, carbon dioxide have features there. And MIRI will have, what else is there? There's water, methane, maybe ammonia. There's all kinds of different things that MIRI can detect, and that this other NIRCam filter. So yeah, excited to start working on those soon and see what the data show us.
So we're at this point in exoplanetary research where you kind of no longer think about them individually, and we're starting to think about them in just en masse, 5,000 plus planets, thousands more candidates. We're starting to get a sense of like, here's where the planets are, here's where they aren't, here's the sizes, here's the distribution. But with atmospheres, we're back to a handful of atmospheres that have actually been studied at this level of detail. So how do you see the science evolving over time as we now have JWST? We've got the aerial telescope coming online in 5 years, hopefully. Do you think we're going to sort of approach that same vast scale of planets in the same way that we just know about planets?
Yeah, I think we're in a really exciting time right now where, like you said, at the start, it was like, we found the 10th exoplanet, woohoo. And we're kind of in that regime of like, we've characterized very well the 10th exoplanet atmosphere, woohoo. And we're going through that very rapid expansion of understanding them. But you raise a good point that it's very costly in terms of telescope time to study these atmospheres, because just finding them is one thing, but if you want to study their atmospheres, you need like 100 times or more like better quality data, and you need spectroscopy, and you need all these other things, which makes it much more expensive in terms of time. So I don't think there'll ever be a day where we've studied every planet's atmosphere. That'll never happen. But with JWST, we're getting a kind of a small population. And I've been very impressed at how many exoplanet observations are being taken by JWST. It's definitely one of the big science drivers for JWST. But there is some limit. Like we need JWST to study galaxies, black holes, stars. There's so many important things, and so there is a limit to what we can use with JWST. With what we're getting with JWST, we are being able to kind of construct a small little population and say like, like I said, WASP-80 seems to be cold enough to have methane. Okay, check. And then we'll try a planet a little hotter, a little bit colder. And then eventually we'll see weird things like a colder planet doesn't have methane, but the hotter one does. And so, okay, maybe there's some other effect that we're not thinking of. And so we'll kind of be playing that game of like putting little pieces of the puzzle, but like really, really precisely measuring a small number of planets. When we get to the aerial era, we'll get poorer quality data, but for vastly more number of planets, and that will really take us into that regime of thinking of planets as an entire population, not individuals. It really takes a mission like Ariel that's almost entirely devoted to exoplanets, that's really devoted to doing things relatively simply in a relatively kind of reproducible way. JWST does 100 different things and does them all well, but that means every different person chooses to set up the telescope in a different way. And so that can kind of make it a little bit hard to compare different planets. Whereas Ariel's kind of just going to cover everything with a blanket and say, like, we studied 1,000 different stars using this technique, and this is what we're seeing. And so, Ariel's going to be a very exciting addition to JWST. JWST will give us that, really, really fine detail on some planets, and Ariel will kind of give us the broader context.
Yeah, I can sort of imagine that. Like right now, you're all in this exploratory phase where you're telling the folks at STSCI, I want to use, I need 9 hours, and you're like, do you want the GRISM? And you're like, sure, why not? I'll take the GRISM, right? Who knows whether it's going to be the right way to go. And then, do you want Miri? It's like it's some kind of menu that you're ordering from. But and each one is, someone's got a hunch about one of these planets, is, meet some kind of criteria. And then you've got the criteria, but then you've also got the technique you're going to try to study it. And then you have something like Ariel comes along and just goes, we looked at them all. Here's all the good stuff. And then you can take all those techniques and apply them in a sort of standardized way to all of these exoplanets. And you don't know which are going to be the good ones until someone even just highlights them. Like right now, you're like, WASP-80b sounded like a good planet. Why not?
Yeah. There's so much opportunity for learning unknown unknowns with that kind of survey of like, when you say like, I want WASP-80b because of these 5 reasons, you're testing a hypothesis, which is a very good thing to do in science. But at some point, you also need to say like, okay, how much can I extrapolate WASP-80 to other planets? And like, there's all of these things that like, I don't really know, but like, I'm confident that there are things that I don't know because there's things I can't explain, and like maybe orbital period matters, or maybe the amount of UV light emitted by the star matters. And like that's really hard to do when you say like, I want this one observation. You can't say like, I want 1,000 planets so that I can understand all of these important factors.
We're in this funny place right now with the observations of the TRAPPIST-1 system. I mean, at this point, we've got great observations of TRAPPIST-1b, TRAPPIST-1c. Both of them are airless supermercuries. We didn't get the Venus analog that we were hoping to see. Did that surprise you? Or do you think that there's some problem with planets around a red dwarf star?
Yeah, so I was a co-author on that TRAPPIST-1b paper, and when I analyzed the first observation, I could see the eclipse in the first observation, and if there was no atmosphere, we expected that each eclipse would probably be able to see the planet significantly, whereas if there was a significant atmosphere, we'd expect we would need all of our eclipses averaged together to finally be able to see the planet. And so when we saw the first one, I was like, oh, that's too bad. This probably doesn't have an atmosphere. And sure enough, you take all the others together and it's like, oh yeah, no, doesn't look good. But one thing to keep in mind too is that these are only single filter at as like a single wavelength or a single chunk of wavelength. And so it's very probable based on these that, yeah, there's probably not an atmosphere, but there's other weird things that can happen that, maybe this wavelength just is misleading us and it looks like there's no atmosphere, but if you look at a different wavelength, maybe there is. So another team is looking at TRAPPIST-1b using a different wavelength to see is doing like eclipse kind of spectroscopy, but only with two wavelengths because it's such a cold and small planet. It's hard to do more than that. A group of us also is getting phase curve observations of both TRAPPIST-1b and C, which is kind of like the middle ground of eclipse and spectroscopy. Eclipse and transits. It's kind of like eclipse, but you're watching the entire orbit, so you are staring at the thing for hours, like days. And you're looking at how the light coming from the planet changes with time, and you get it in a transit and an eclipse. You get all of the whole thing, and so that kind of gives us another insight into what the planet's atmospheres may or may not be like. I mean, to say that they don't have atmospheres is not exactly true. Like, it's going to have the ever most thinnest atmosphere. Like you throw a bare rock out into space, it'll have something. It's just not going to be appreciable. Yeah, we don't know exactly how thin an atmosphere it might have, and so these will help. But yeah, you raised a good point of is there issues with being a rocky planet around an M star? Can they have atmospheres? That's a big question. Like I said earlier, M dwarfs have a lot of rocky planets around them, and so that's exciting because, yeah, if we think life has to form on a rocky planet, well, there's a whole lot of rocky planets around M stars, and it's a lot easier to characterize the planets around M stars. Then we should really be studying these. But there's kind of two ways you can think about this. One is if like, it's not the right number, but if 90% of rocky planets are around M stars, why are we not? Why are we around a sun-like star? And so it's one of the anthropic principles that like you should expect to find yourself in the most average place because you're not special. If there was life around every planet, you should find yourself on the most typical planet. So if life were common around M stars, then we should probably be around an M star, and it's weird that we're not. Another thing, a reason that might happen is that M dwarfs they're colder. So to be habitable, you have to be very close to the star. And that also means that you're much closer to all the UV light and UV X-rays, all the nasty stuff that are emitted by stars. And then even worse than that, M dwarfs, especially early on in their life, emit way more UV. And so if your life, it's not fun to be baked by UV and X-rays. Some people think, we need UV and X-rays to make life, so maybe that just helps kickstart life. But you also need not too much UV, otherwise you kill life. And so, yeah, maybe there's danger to life in that sense, but there might also be danger to atmospheres because all that UV ends up stripping the atmospheres off of the planets. And so, yeah, you need to be kind of far enough away to not lose your atmosphere, but or you lose your atmosphere, and then you have to have kind of like volcanoes or whatever, some process that brings gases out of the interior of the planet to the surface. And then you probably lose all of that because the UV lasts for so long of the star's life. And you kind of just continuously losing your atmosphere. And the question is like, is there a point at which you can finally stop losing your atmosphere and have an atmosphere and develop life or anything like that? And that's a big unknown.
Yeah, I saw a paper just a couple of days ago where they did the math on the mass loss that would be expected from TRAPPIST-1c, and they didn't think you could blame the star, that it wouldn't be enough to completely destroy the atmosphere of like some kind of Venus analog. So maybe it never had an atmosphere to begin with, that was its It's always
Yeah,
sucks.
there's all kinds of things that can lose an atmosphere. I mean, I'm no expert on this, but yeah, things like um, meteors hitting a planet can end up putting a lot of heat into the atmosphere, and that kind of can boil it off. There's all kinds of different things that can cause you to lose an atmosphere, and yeah, like you always form with at least a little bit of hydrogen in your atmosphere, and like Earth probably would have formed with some hydrogen, and then it would have lost that too. But then it should have, it obviously produced nitrogen dominated with some oxygen, carbon stuff. Um, so it's that kind of process of lose, reintroduce, kind of weird mixture, and there's a lot of unknowns. We don't know these stars and planets well enough to really know, but yeah, as we study these planets and stars more, we'll hopefully understand. One other thing I wanted to point out too is that TRAPPIST-1 is a very unusual M star. It's not just an M star. It's like one of the coldest M stars that is still a star. It's almost a brown dwarf, and so that's important in a lot of these factors that I was talking about. You really, really have to be close to your star to have enough sunlight or whatever to be warm and be habitable. And so, what we learned from TRAPPIST-1 can't necessarily be applied to other stars, because we're talking about like huge differences, like a hot M dwarf to a cold M dwarf. They're really not that similar. There's a lot of discrepancy between them.
Yeah, like TRAPPIST-1 was surprising to find, and we haven't heard of a bunch of other ones that are very similar to TRAPPIST-1, even though we've got all of these instruments that are looking. It's still one of the most exciting places to look. When can we expect to find out about the observations from TRAPPIST-D through F, which are the ones in the habitable zone?
Yeah, so I'm not on any of those teams, so I don't know for sure. I expect in the next year, a lot of those papers will come out. Many observations have been taken. I think one of them might already be out in press or may already be published. I guess that was TRAPPIST-1b, probably.
There was the B and C have been observed, and we're waiting for D. Yeah. But I wonder, there's like a 1-year timeline, right? So at a certain point, they're going to have to make their data available on the server. Would you take a peek?
It's a challenging thing. Like we've already seen for the planets that have been observed, there's stellar flares, there's like star spots that are like colder and make it kind of trick you into thinking like, oh, look, there's water. But it's like, oh no, it's probably water in the star's atmosphere, because again, the star is so cold that it can have things that you would expect in the planet's atmosphere, which just like makes it so much harder to tell what's coming from where. I'm sure all of these teams are working very hard to do their best they're not trying to sit on data, but it takes a lot of work, and you could do the irresponsible thing and say like, oh, cool, I found water, but no one wants to publish a paper that's like immediately proven wrong. And so like they're doing the hard, good work of trying to do the right thing, trying to be really, really careful and do the best they possibly can to, publish good results.
Yeah, that makes a ton of sense. That, we've seen the Viking experiment, Alan Hill's meteorite, phosphine on Venus. Like, we know how this story goes. Room temperature superconductor, cold fusion, like, faster than light neutrinos. Like, at a certain point, you wait. The more exciting the result you think you're sitting on, the more you wait, and the more you're careful, and the more you ask other people to check and double check and so on. And that does definitely explain to me why it's taking so long. But then maybe that means, if they got a null result, they would have gone, whatever, we'll put it out. But the fact they didn't get a null result means they're being really careful. So, but we could speculate forever. So I want to talk about the Holy Grail, and that is hoping to find some kind of interesting biosignature in the atmosphere of an exoplanet. Do you feel like the astronomical community is ready to, do they even know what they're looking for yet?
That's a really tough question and a good question. I'd say we have beginning ideas. There's people that are working on, posing good questions, good, like, testable hypotheses. But yeah, I think it's going to take a lot of time and effort, and it's going to be a good while before there's any kind of like, oh, we've definitely found life. I think well before the astronomical community agrees that we found life, there'll be a paper saying we found life, and it'll probably go back and forth. It'll probably turn into one of these messy things, and we're all trying to not have those kind of circumstances. But there's going to be someday someone finds a cool molecule and say, okay, maybe it's life. But there's like so many preconceived notions in our brains that are like hard to spell out. And so like, let's take methane again. It's definitely not life in WASP-80, but it's caused by life on Earth. And so maybe one day we'll find methane on a planet and we'll be like, oh, cool, methane, maybe there's life. And that'll kind of be a paper someday. And it's like, okay, well, no, it's probably not, because there's all these different ways. But other molecules can be much more tricky, where like on Earth we know a certain molecule, whatever, is only produced by life. There's no way of making it. But this other planet is not Earth, and so maybe it has a different kind of atmosphere that is able to support that molecule. Maybe there's a lot more of a certain atom, like some weird atom that we don't have much of here. Maybe there's just tons and tons of volcanoes spewing out stuff. Or maybe there was a huge ocean and all that ocean evaporated, and so you're left with like tons of oxygen in the atmosphere, which, like, again, a lot of the oxygen, like molecular oxygen on Earth, is produced by life. And so, cool, you found oxygen, but no, that's caused from evaporating oceans. And so it's going to be a lot of time. Like, we're looking for exciting things, but it's going to take a lot of time and careful thought of, when we find something, ruling it out. That it's you don't want to say it's aliens until you know for sure that it's aliens. And so, like, people will find something and say, this is interesting, we don't know what it is. And then it's kind of punting it over to the theorists and saying, like, try everything you can possibly think of to figure out why this isn't aliens, and like, what other ways could this molecule be made. And it's going to be a lot of that kind of exchange of like observers saying, we think we found this cool thing, modeling people saying, no, that's probably not that, or we need more context. Context is the thing we need the most, is context. Like, I've been talking about methane and oxygen and stuff. Typically, the biosignature people talk about for life on Earth is methane and oxygen, because methane and oxygen interact to make CO2 and water, and so you don't expect the two of them together. And so you need those two detections, methane and oxygen, in a planet of the right temperature where those things shouldn't form naturally. And so there's all of those pieces of context. And so telescopes like JWST will get broad spectrum, which helps us. But we also need things like transits and eclipses to know how hot it is and what the planet looks like kind of all over the planet. And so it's all those pieces of context before we really can begin to say, like, oh, well, we see methane and oxygen, but we also see some other third thing that tells us, okay, it's actually this other thing that's going on. It's kind of putting all those pieces together.
And do you think that, like, it will be this, like, collection of observation? So it's not just, we found ozone, therefore life, or we found oxygen, therefore life. We found this, that, we found these 5 chemicals that shouldn't be interacting in a way without being replenished, and at the temperatures we don't know of any way but with life.
Yeah,
That's where
I
you start
think the
thinking.
only case in which a single kind of datum would tell us that we found life is through something like SETI, where like all of a sudden we catch someone's television signal from another planet, and like we see their video output. Like I think that's the only way in which a single observation would say like, oh, well, yeah, they're talking to us. Everything else is going to be a lot of like stitching a lot of different pieces together to rule out anything that's not life, because extraordinary claims require extraordinary evidence, and so it's going to take a lot of evidence before the astronomy community says, yeah, there's probably life. It's yeah.
What do you think about like searching for technosignatures, like say chlorofluorocarbons, things like that? I mean, those seem like they would be a hard to get naturally.
Yeah, there's things like that are a possibility. Again, there's the caveats of like, you never know what weird UV stuff can do. But yeah, the bigger the molecule, the more complex it is, the more likely that some being had to exert force to make that molecule. But that said, there's like all kinds of super bizarre molecules that are just formed naturally out in complete emptiness of space, like in the middle of galaxies. You have all of these. There's complicated molecules that form just out in the emptiness of space, that just naturally form over billions of years, whatever. In planetary atmospheres, there's a lot more molecules flying around, and so complicated molecules are harder to survive because any little hydrogen atom can just come in and like bash them to pieces. And so yeah, big weird molecules are a good step in the right direction, but yeah, you'll still need some context. And the other thing is these complicated molecules are typically, they have relatively small features, and it's not like you're going to have chlorofluorocarbons as like the entire atmosphere unless the aliens just like polluted themselves to death, in which case like we might be able to eventually see that signature with enough observations. But yeah, like on Earth, chlorofluorocarbons are a tiny, tiny, tiny fraction of the Earth's atmosphere, and they only affect a very small region of wavelengths. And so, yeah, it's not just detect like on Earth. If you spent enough time, whatever, eventually you begin seeing the main things. You'd see oxygen, you'd see carbon dioxide, and it would take you so much time to eventually be able to see chlorofluorocarbons. And so yeah, it's that trade-off of like you need something that's abundant, but like doesn't kill the aliens to be that abundant, and needs to be obviously produced by life. And so it's a hard thing to do.
Well, I mean, one of the questions that I have is like, you can determine the existence of chemicals in the atmosphere. Like you detect the presence of methane through its absorption of the sunlight. But can you get a sense of how much there is, or how much there is in proportion to other chemicals and elements in the atmosphere of a planet?
Yeah, so yeah, you definitely can. And again, to do that, you kind of need context. The broader wavelength range you have, you start getting like one water bump and then another water bump and then several more water bumps, and then you get a couple methane bumps and a couple whatever bumps, and having each feature is kind of a little bit dependent on the temperature and the abundance of that molecule, and that it's not like water is over here and methane's over here. There's all this messy mixing of different things. And so having a broad wavelength range allows you to like really clearly say, okay, this feature is like the shape is caused by water, this shape is caused by methane. And then you can do exactly what you said. So the way you do this is you model a atmosphere of what it might look like, and you put like a teaspoon of this, a tablespoon of that, and then you see what the light would look like through it, and then you kind of twist those knobs of adding different amounts of different molecules, and then you kind of match the shape of the spectrum. And so, yeah, in doing so, you get ratios like carbon to oxygen ratios, or iron to hydrogen, or water to methane. And yeah, eventually you get enough of those pieces that you can begin to say, like, oh, there's this amount of like carbon molecules, yeah, per box of whatever.
Like 20% of the atmosphere is carbon dioxide and 15% is nitrogen, or something like that. Could you get to that level of specificity?
Yeah, that you work towards that. With our particular data set, we had just a pretty small piece, and so we don't have enough context. But yeah, as we get more data, it'll be a lot easier to say, yeah, so much of the atmosphere is.
But it's like a Sudoku puzzle, kind of.
Yeah, exactly. Like you're starting to rule where numbers can't be and where numbers could be.
Right. That's interesting. So what are you obsessed with right now?
I think, kind of going back to this discussion of eclipse mapping we had, is the study of planets not as kind of one-dimensional things. So like when we talk about transits, we talk about like the atmosphere, and it's like, well, there's the atmosphere is a whole planet size. Like there's this part of the atmosphere, that part, and because one side of the atmosphere gets baked in starlight and one side is just looking at the darkness of space, you have all this different, all the enormous differences. Like the two sides of the planet, to someone standing on them or floating in them or whatever, would seem like completely different planets. They're completely unalike. And so talking about the planet's atmosphere is a really simplification. Like there's a lot more nuance to it. And before JWST, that was largely the best we could do, though, is like we might talk about eclipse and transit and kind of like talk about them as like different parts of the planet, but the transit is made up of a little ring around the whole planet, and the eclipse is the whole dayside face of the planet. And so using techniques like eclipse mapping or phase curves, or even fancier techniques to kind of study different parts of the transit atmosphere, you can, when the planet starts to transit, one half of the atmosphere starts to transit first, and then the last half is just the last part of the atmosphere. And so kind of using all these kind of like one-up techniques, you're still using the same general techniques, but you're doing it in a new way that really lets you see planets in 3 dimensions, or even 4 dimensions if you look at them changing in time. So again, I've been talking about the atmosphere, but Earth doesn't have a constant atmosphere. There's clouds, there's rain, there's snow. And they're so close to their star that their weather should probably be fairly, like, every day is sunny on one side and every day is cloudy in another spot, and it kind of doesn't change. But we don't know that. That's largely just based on models and what we think. And we think, oh, it shouldn't change that much. But we haven't measured that. And that kind of goes back to this importance of telescopes like Ariel, which will do a big survey of different things, and some of them do repeats. Is if we just look at an individual planet once, we don't know if we just caught a weird snapshot in time and like it's not normally like that. There was just a rainy day, or if it's just like a weird planet compared to its neighbors. And so yeah, really studying planets more holistically, I'm excited about.
Like, I wonder if you had a telescope, like say you were able to wrest control of JWST and only you got to use it for years at a time. And if there was a planet that had some kind of eccentricity in its orbit, then it's sort of which part of the star it's passing in front of will change over time as it's interacting with the star. And I wonder then if you could see times when I sort of think about, when we see the moon pass in front of the sun, sometimes it's a full transit, sometimes we get a partial eclipse. and each one has its value. And I wonder, if you could get times where the planet is just grazing the bottom of the star, well, now you're only seeing the South Pole, for example. And now you're able to sort of go, we can see polar vortexes and various kinds of weather systems just at the South Pole, which is different than when it's transiting and we're seeing the equatorial regions perfectly, the beginning and the end. So I wonder if we found an interesting enough world that it would be worth just dedicating mountains and mountains of time, one telescope to study it.
Yeah, so the issue is that orbits on the human lifetime really don't change. Like there's kind of two issues. That orbits, like Mercury's orbit does precess, and so it has a kind of close point and it changes over time, but it's not relevant on a human timescale. And so you can't really just wait for it to change. And the other issue is if you have an eccentric planet, it has a much longer orbital period. It takes a much longer to come back around. And so, to observe an eccentric planet, especially a very eccentric planet, you might have one chance in an entire year. And otherwise, it's just so far away from the star that you can't possibly. Well, but there's like no use of observing it when it's that far away from the star because it's so cold.
You can let other people borrow your telescope. That's fine.
Yeah, you can let it out. Yeah. But so I think the more favorable thing is just the many planets population technique, because kind of astronomers have adopted that mentality throughout everything, because we want to know everything from the Big Bang to what's going to happen tomorrow. And so you can't do that with a single observation, but you can look at many different objects, and by kind of stitching kind of a quilt work of different observations together, you can build a timeline. And so similarly, by observing many different planets that are all kind of similar in different ways, you can begin to understand, how one planet might vary, even if you haven't observed that planet. By observing tens or hundreds of planets like it, you begin to understand how to piece it together.
That's interesting. Well, Taylor, thank you so much for your time. Congratulations on detecting methane in the atmosphere of an exoplanet with JWST. I look forward to this being one of hundreds that we know of.
Yeah, thank you very much.
I'm going to give you some closing thoughts about this conversation, but first I'd like to thank our patrons. Thanks to Hey Twyla, Dougie Stewart, Stephen Krasaki, David Richards, Mark Anstis, Joel Yancey, Antonio Lofilara, Dustin Cable, Vlad Shiplin, Modso, George, David Giltonet, Andrew Gross, Jeremy Mattern, Josh Schultz, and Jordan Young, who support us at the Master of the Universe level, and all of our other supporters on Patreon. Well, this was great. This was one of the conversations that I've been wanting to have about somebody who has expertise in studying exoplanet atmospheres. And I had a bunch of questions that I didn't really know the answer to, and I learned a bunch of new things about this method of transiting a planet both sort of in front of the star but also behind the star, and how you get a different perspective. You get start to map interesting characteristics about the atmosphere, and how we're moving from these just one-off observations of planets into this new world where we're going to be able to see thousands of exoplanet atmospheres and get a sense just in general about how these planets are. And then of course the goal is to find an example of an Earth-sized world orbiting around a sun-like star. Wouldn't that be amazing? Be able to study its atmosphere and try to begin the argument at least about whether or not there's life there. Now, obviously, I've done a ton of interviews on this very topic, so I'm just going to put links to two of them here that you can use to follow this conversation more. But really exciting to be able to see the detection of methane this quickly after JWST launched. We'll see you next time.